All right, guys. Let's see if this works. The last couple of lecture recordings have gotten messed up, so I keep trying to reconfigure everything. We'll see if this one is successful or not. But a reminder that you are responsible for what happens in this classroom, even if the lecture recording gets screwed up. So, nice to see everybody. Is this mic like extra loud today? I don't really know what to do about that. I can do that, but like you're still gonna hear it echoing against my shirt. That's a little better. Okay. Right. So in terms of announcements and things, you guys have a homework. Many of you were in my office hours yesterday, which is fantastic. I also noticed that Mark's office hours are underpopulated, so you guys should go get, he'll give you answers too. You don't have to come to me. So if you're looking for individualized help, might I suggest going to my colleague? Although you are, of course, welcome to my office hours as well, but that's too late for the current homework. So finish that up, and then the next one will go out soon. Basically, at this point in class, you have everything you need to do that homework minus one object, which is the SVD for a single problem. If you peek forward in the chapter on SVD to the section on Procruste's problem, you'll basically see it's identical to the homework problem. And if you weren't in lecture to hear that, then you'll struggle through that homework problem. Beyond that, don't forget your weekly quizzes, and be cognizant that this class does have a midterm that will happen eventually. Any questions, comments, concerns? Yeah.
Do you have any like practice exams for the midterm?
We have many. So if you remind me, I can post this class has only been offered once at MIT in the past, so there's one direct analog, and then there's a bunch from when I used to teach a very similar class at Stanford. Here's the thing, every time we teach, things just don't align perfectly, so I always get the same questions about practice exam, which is like, we haven't covered this. Why is it on the practice exam? It's because it's not the same class. So obviously, if there's a question on a topic that we haven't covered, then like it won't be on the midterm. That said, the midterm will cover everything up to and including the lecture immediately previous to the midterm. If that scares you, the good news is that you can certainly look ahead in the book chapters. All right, any other questions? Cool. All right, guys, so today we are going to continue talking about eigenvalues because that's what we're doing in our last couple lectures here. So in case you haven't figured it out by now, essentially our goal is to basically wrap up our discussion of linear algebra problems in probably today's lecture and the next one. And then finally, we will talk about nonlinearities, which is good because these days we live in a very nonlinearity intensive world. But what we're going to see is that the algorithms that we'll be deriving for the second half of this course, which are all these fancy, nonlinear optimization and roof finding and integration and differentiation, all this kind of stuff, basically depend very strongly on the fundamentals that we've developed in the first part of this course, which makes good sense, right? I mean, basically, the vast majority of numerical algorithms out there in the world at some point invoke Taylor's theorem. And then as soon as you do that, you're back in the kind of linear algebra quadratic form regime. And that's really all there is to it. But in any event, today we're going to continue with eigenvalue problems, and hopefully we're going to introduce our very last matrix factorization in this class. That's not to say that there aren't others out there. There are actually many. But we're going to talk about the SVD, which is sort of like the big kahuna of matrix factorizations. On the other hand, it's expensive to compute, right? So like it solves most of our numerical problems out there in the world that involve linear algebra. But on the other hand, the SVD is sort of the most sort of computationally expensive thing to actually extract. Okay? So if you recall in our previous lecture, what did we do? Essentially, we derived a bunch of different algorithms for computing more or less one eigenvector of a matrix at a time. And all of them were based on a really goofy fact, which is that if I take an arbitrary vector and I just multiply a bunch of times by our matrix, then what happens is we kind of amplify the component parallel to the largest eigenvalue. Right? And so that technique was called eigenvalue iteration. And then essentially all of the other algorithms that we derived after eigenvalue iteration were more or less variations of that story where eigenvalue iteration was left alone, and what we did was modified the matrix that we multiplied by, which essentially like reordered the eigenvalues. So for example, remember if the eigenvalues are like lambda 1 through lambda n of a matrix, then the eigenvalues of its inverse, assuming that it's a full set of eigenvalues, are like the reciprocals, so the order flipped, right? And when we did that, of course, now when we do eigenvalue iteration on the inverse of the matrix, what we get is the biggest eigenvalue of the inverse, which is 1 over the smallest eigenvalue of the original guy. So now we can kind of at least hit two ends of the spectrum. And then we talked about shifted iteration, which can target things in between. Hopefully that story rings a bell. So today, in the first half of the lecture, today what we're going to talk about are strategies for computing more than one eigenvector, which we began to suggest at the end of last class, and then I ran out of time. And then what we're going to do after that is talk about getting all of the eigenvectors in one very expensive shot, which does appear in certain applications, usually in like small to medium-sized matrices. You shouldn't be doing this for big guys. And then after that, if we have time, we're going to motivate the SVD, which is basically an extension of the eigenvalue problem. So this is an ambitious lecture. We'll see how far we get today. Okay, so recall that essentially what we left off with in our previous lecture were a bunch of variations of algorithms that take a matrix A and then give you back lambda max and x max. That's kind of a pair, basically all by doing the same thing, which is just multiplying a bunch of times by A. So I think it's worth noting that there's a lot of different strategies. Like, let's say that I just want two eigenvectors, which is actually very common, that like essentially all I really want are like the 100 smallest or largest eigenvectors is like, I would argue probably the most common application of eigenvalue problem. So for example, like in diffusion maps, embeddings, all these kinds of things, essentially you only want the number of eigenvalues that are equal to the sort of size of your embedding. And so in that particular case, maybe what we really want is like lambda 1 through lambda k, where k is much less than the size of your matrix, but also probably substantially larger than 1, right? And so we talked last time about one strategy for doing that, if you recall, where essentially we compute the biggest eigenvector, like x1, right? And then what I argued to you is that if we conjugate our matrix like P transpose A P by this matrix P, which projects out x, right? So remember that like P equals, I guess, I minus XX transpose, something like that. And then essentially what's left, like what is this matrix? It basically, at least when A is symmetric, has the same eigenvectors as P, but I took the eigenvalue corresponding to X and I zeroed it out, right? So now if I do eigenvalue iteration on this new guy, P transpose AP, then what happens is I get the second largest eigenvalue of A because the largest one is now 0. Does that make sense? Now, this algorithm is perfectly fine, and indeed that's really how a lot of people calculate multiple eigenvectors. But it feels a little uncomfortable for a few reasons. I mean, essentially, notice that like this matrix is kind of secretly n-1 dimensional. Do you see that? That like really, like we already know its action on one of the x's. So like when we're multiplying by this matrix a bunch of times, somehow it feels wasteful, right? Like we're dealing with this x subspace, which we know we don't need. Yeah. And so to conclude our discussion of just like getting one eigenvector at a time, I think it's worth mentioning one other strategy, which is kind of cool because it builds on an algorithm that we derived a couple lectures ago, which is as follows. So first of all, we're going to make a quick definition, which is what's on the slide. The two matrices are similar if there exists a T so that B, so if A and B are similar, then B is equal to T inverse AT. Read the slides, don't trust what comes out of my mouth, okay? And there's a very simple proposition, which is that similar matrices have the same eigenvalues. Yeah. Do we want to prove that? We can do it really quick. So let's say that I have an eigenvector like T -1 A T x equals lambda x, like that. Well, here's the thing I can do. Well, I can do A tx equals lambda tx, just by multiplying both sides by t. And let's parenthesize it like this. Okay? And if we can call this vector tx, we can just give it a name, like y. So notice that, what did I show? I showed that ay is equal to lambda y. So notice that, and basically we could read this proof forward and backward. Essentially what it's saying is I can take any eigenvector of T inverse AT and map it to an eigenvector of A and vice versa by transforming by T. By the way, a sanity check. A thing you should check when you're deriving these kinds of eigenvalue algorithms, like this kind of argument, is like, well, what if this thing equals 0? But notice in this case, I've kind of assumed T is invertible, so that can't happen. Okay. So hopefully we all believe me that essentially similar matrices have identical eigenvalues. I see. They don't have the same eigenvectors, so we have to be a little bit careful. And so that suggests that we can do something kind of similar to our strategy for LU factorization. Like, what do we do in LU factorization? We just took our matrix and we started like applying stuff to it that preserved the structure we care about, in that case, like AX equals B, and then tried to reduce it to a simpler form. Well, now we have some transformation that leaves the stuff we care about alone, in this case, the set of eigenvalues. So our strategy is going to be to try to apply a bunch of similarity transforms that make our eigenvalue problem easier and easier. Alice, yes? It's absolutely a change of basis. Yeah, exactly. That's a perfectly reasonable perspective. All we've done is taken our eigenvalue problem and kind of rotated it. Of course, if T is like a shear or a flip, then the picture you have to draw is a little annoying, but yeah, that's totally reasonable. Any other questions? Cool. So our eigenvalue iteration algorithm would be awfully expensive if every time I wanted to do this, I had to compute the inverse of a matrix, right? And so a reasonable question you might ask out of laziness, which we already kind of did when we talked about QR, is like what's a reasonable class of matrices that are easy to invert? And I think the class that usually comes to mind are orthogonal matrices, right? So orthogonal matrices are exactly the ones that satisfy, at least when they're square, this relationship Q inverse equals Q transpose. Computing transpose isn't so bad, it's just the inverse part that's kind of annoying, right? And so basically our remainder of our eigenvalue iteration algorithms that we'll talk about in today's lecture basically involve taking your matrix and conjugating it by well-chosen Qs so that the eigenstructure slowly gets revealed. Now, what's a little bit different between this and like LU and Cholesky is that it's going to be iterative. We're going to converge on a nice-looking matrix, whereas before we were able to just target it in a finite number of steps. Incidentally, for those of you who are excited about advanced topics, you can search, there's a really cool algorithm, which is what's really implemented in these software libraries, called reduction to tri-diagonal form. So it turns out with a finite number of Qs, you can take any matrix and map it to one which is almost revealing the eigenstructure. Essentially, it has 3 things down the diagonal and nothing else. It turns out you can do that with like sort of steps that look kind of like Gaussian elimination. But going from this to the eigenvalue still requires an iterative algorithm. We're not going to talk about this strategy in this class because it's a bit picky. But the reason to do this, remember that eigenvalue iteration, what is the cost of each step? It's a matrix multiply, right? So if I can get my matrix to just have 3 diagonals and have the same eigenvalue, I'm doing pretty well, because now it's like order n time per step of iteration instead of n squared. So anyway, if you're curious, typically like the real software packages out there, they kind of take place in 2 phases. First they take your matrix, they reduce it to tri-diagonal form, and then they do eigenvalue iteration so that it's cheaper. But we're going to ignore that for now. Okay, so in any event, my high level point was that if we conjugate with stuff, we leave the eigenvalues alone, and moreover, if we conjugate with a orthogonal matrix, then things are particularly easy. So here's going to be one sneaky trick which we can use to do this sort of deflation strategy where you compute one eigenvector, you get rid of it, and now what we're going to do is do eigenvalue iteration but on a smaller matrix. So this is kind of fun. So this is one of these algorithms where as you compute more and more eigenvectors, the iteration itself gets faster, which is kind of cool. It like accelerates. Which is as follows. Remember, we defined in our lecture on QR a very particular matrix that was the householder matrix. You guys remember that guy? And what did the householder matrix do? It basically takes, called it H for householder, and we designed it so that we can take some vector x and multiply it by some, I can take x and multiply by h, get some constant factor of the first standard basis. That make sense? So here's a really cool thing. I love this little trick. So let's think about what happens if I take H and I conjugate it by the householder matrix. So in particular, I'm going to take H, A, H transpose, and I'm going to multiply it by E1. Cool? This feels weird, but like we can certainly do it. So remember that householder matrices are orthogonal. So H transpose E1 is the same as H inverse E1, right? So if Hx is some multiple, and in fact, I think we can design it so that there's no constant there, just to be lazy. So then what's going to be H transpose E1? Any guess? Yes? X, that's right. In some sense, there's only so many symbols on the board. Yeah, that's absolutely right. So we have H, A, X, hex. Now, what's A times X by definition, if I choose to be the eigenvector? lambda x, right? So this is lambda hx. Hx is E1. So what did I just prove? I showed that the first standard basis vector is an eigenvector of this guy with eigenvalue lambda. Isn't that cool? So let's think about what that implies for an algorithm. I can compute one eigenvector x, and now I can take A, the original guy whose eigenvalues I wanted to compute, and I can conjugate it by h. When I say conjugate, by the way, I mean this thing. Okay? And let's think about what that matrix has to look like. By the way, this is on the slides too. Yeah. Well, if you think about it, well, we just showed that if we multiply it by E1, we get some multiple of E1, right? So by the way, in general, do you guys see that if I multiply a matrix by E1, what I'm really doing is pulling out its first column? So what did I just show is the first column of this matrix? Yeah. Yeah, it's just lambda E1, right? So in particular, if I kind of think about what this matrix looks like, I've got a lambda and then a bunch of zeros. By the way, it's symmetric, so I also have a bunch of zeros this way. That makes sense? What's in the rest of this matrix? Well, I don't really know. A bunch of stuff. However, if you think about it, the eigenvalues of this block are exactly the remaining eigenvalues of A. Yeah? And so this is called householder deflation. It's a really clever algorithm. You compute one eigenvector, you conjugate by the householder matrix, and that is guaranteed to give you a matrix of this form. Now you discard the first row and column. You now have an n-1 by n-1 matrix, and you just do the whole thing again to get the next biggest eigenvalue. You can iterate. Does that make sense? So this is one strategy that's a little bit less wasteful for computing one eigenvalue at a time by essentially compute the eigenvalue, deflate, and then keep going. Cool? Yes?
Is this what's used to be more just iteratively compute eigenvalues?
This is one strategy that's used. Yeah, there's a bunch of algorithms out there. I think the Correlus subspace methods are a little more common, but there's some extension of this kind of logic. Yes?
How do we know it's picking out the biggest eigenvalue?
How do we know it's picking out the biggest eigenvalue? We don't. What we know is that we computed some lambda, whatever it was. In fact, this strategy works for the biggest or the smallest, and the conjugating by this thing removes whatever that was and then leaves what's left. Yeah, good question. Yes. Yes, A needs to be symmetric for this particular strategy to work. Although I think actually, now that I think about it, actually, I don't know if that's actually true, because I guess generically, if you do that, so if A is not symmetric, this argument still holds. So I guess what you wouldn't know is that this block is all 0, but I believe it's still enough to convince yourself. This is not, like, my proof doesn't hold anymore. But I believe the deflation will still end up working. You could just discard the first row, but I'd have to think about it. Yeah, it's a good question. I'll have to come back to you. Yes, Hamid.
Yeah, I was just trying to see how to getting a more efficient algorithm out of this, because it seems like we've nicked off a lot of the
Well, 3, right? Which is a lot less than infinity. Which is what you need in principle to get an eigenvalue, right? So essentially, this deflation step, if you're only going to get like 2 eigenvectors, I agree with you, it's probably not very useful. But if you want like a few hundred, then it becomes more useful. Now, there are more advanced algorithms out there that might get like 2 or 3 at a time. So like this, in that case, you probably like compute a little block of eigenvalues, remove them, and then decrease by more than 1 at a time. Yeah. But like essentially, if you're computing a ton of eigenvectors, the point is that chances are the dominant eigenvector will converge first, and that like at that point you might as well deflate and remove it, and then your matrix multiplies are cheaper.
I guess, like, can't you always project, like let's say we're running this iterative algorithm but for 3 times.
Yeah.
Can't you always, like, you have like a set of vectors, can't you always like project onto that space when you're doing this?
You can, but there's a bit of a chicken and egg problem. Like you don't know that those vectors are the eigenvectors until you've converged, right? So if you project too early, then you've thrown out information that's relevant to exactly the problem you're trying to solve. Yeah, these things are tricky. Like you have to think about like there's a bunch of different rates of convergence that are interacting with one another here, right? Like you could imagine like if lambda is not known with a whole lot of precision, and now I do this deflation, then what just happened to the eigenvalue of the lower block is a totally reasonable question, and one that we won't think about too carefully. Yeah. All right, good. So I'm glad you guys are thinking critically about this stuff. These things are really hard to implement. Like if you look at implementation of numerical software, like you might notice like in this class we cover the big idea, and then when you look at the code, there's like a billion different tolerances and little boundary cases it has to deal with, and this is certainly the kind of thing that I think you guys are hinting at. Yeah. Okay, so far we've talked about strategies for getting one eigenvalue at a time, and the good news is that you know, essentially, this particular technique at least isn't wasteful in the sense that, like, once I've found an eigenvalue, I can project out that space and then have a problem of size n-1. But of course, if I want the full set of eigenvectors, like, there are kind of two possible issues with this. For one, I mean, it seems awfully expensive to compute one eigenvalue at a time with a ton of iterations, throw it away, and then do the whole algorithm again n times feels kind of wasteful. And moreover, as I kind of pointed out, like chances are this lambda is slightly inaccurate because that's the deal in numerical methods. So when I deflated, now this thing has slightly wrong eigenvalues. When I deflate again, it has even more wrong eigenvalues. So the more times I do this, the less accurate my eigenvalues get. And that could be kind of problematic. So one could ask, in an application where I want basically the whole eigenspace, should I be doing something else? Yeah. And so that is what we're going to address next. And we're going to do it with an algorithm that fits in 3 lines of code and then takes a lot of justification, and probably I'm going to get wrong midway through class and give up. Cool? All right. So hopefully what you guys have seen from our discussion so far is that, like, if we can, conjugating by a orthogonal matrix is kind of nice because then we don't have to invert. We can just have a transpose. And so, like, generically, let's say just like experimentally for now. Might say, like, if I just have a generic matrix A and I want to do something to A to try and reveal its eigenstructure, what thing should I conjugate by? Right? It's like kind of the high-level question. Similar to, like, when I'm designing Gaussian elimination, eventually we kind of converged on, like, forward substitution and diagonal things as being the right matrices. But for eigenvalue problem, it's not so obvious, right? Like what should be our building block? Like, there's nothing really staring us in the face, or space, whatever. Okay. So here's kind of a weird experimental thing you could do. And I really believe, actually, I was trying to dig through the history a little bit last night in the middle of the night. And as far as I can tell, this was the history of this algorithm. Like, somebody just, like, had some vibe, like, what is this? Maybe this is the right thing to do. And tried it out, and it turned out to work. Oh no, are my notes gone? That's not good. Okay. Well, all right, team, we're doing it live. Great. Love that. Which is as follows. So essentially, okay, there we go. Let's say that I have such a generic matrix A. By the way, we are going to assume that it is symmetric and has no repeated eigenvalues. The second assumption can easily be relaxed. The first one, not so much. And now our task is going to be a little bit different. It's going to be to compute the full set of eigenvalues in a shot. So here's like a weird thing that somebody out there apparently tried, which is as follows. I take A and I factor it using the QR factorization, because somehow, like, I need some orthogonal matrix to conjugate this thing by, and the kind of the only one we know of in this class so far is this, it comes from QR, right? And here's the kind of bizarre thing that turns out to work, spoiler alert, which is to take A and replace it from QR to RQ. This is like one of these algorithms that just, like, looks really mystical. And then you just iterate these 2 steps. In fact, you should all just, like, pull up a Python notebook really quick and try this, and you'll see what'll happen is that R is going to converge to a diagonal matrix of eigenvalues, and Q will converge to the set of eigenvectors. This is just miraculous. Like, you guys should be excited because this is so cool. And it, like, glues together all the things we've done in this class. Okay, yes? I mean, literally, I have this iteration. I start with A, and then I have a big for loop. And I just repeatedly do these 2 things. I take A, I factor it, and then I replace A with the product of the factors in reverse order. And I just do that over and over and over again. And what you'll see is that R becomes diagonal and Q becomes a matrix of eigenvectors. Yes, Alice? There are so many geometric interpretations, and that's what we're going to cover next. Yeah. So far this just is mystical, a weird algorithm, but it turns out that actually this is doing something very simple behind the scenes, which we're going to try and justify a few different ways. So we're not going to prove convergence in the totally formal sense, but we're going to kind of get to convergence vibes of this particular algorithm, because actually proving convergence requires some nasty bounds that we don't want to think about. So I hope you guys are all excited, because this is so cool. It's like 3 lines of code. It's like amazing that this works. Okay. So here is maybe one way to kind of understand this technique from like 1,000 miles away. So far, like, this is our technique. And remember, I keep talking about conjugation, but then we didn't actually do conjugation. Let's say that I took A and I conjugated it by Q, right? So in particular, I did Q transpose A Q, like that. And, well, we already know that A is equal to QR, like that. So notice, from this perspective, when I flip the order of R and Q, really what I'm doing is conjugating by the columns of Q, right? So at the very least, I can at least argue one thing now, which is that one step of this algorithm doesn't mess with the eigenvalues, right? That's what we've proven so far. Moreover, here's going to be some rough way to think about it that we're going to fill in today in today's lecture, to kind of go to Alice's question here. Essentially, what we're going to show is that this is kind of like computing the QR factorization of a big exponent of A. And if you think about what does eigenvalue iteration do, it just takes A and it multiplies by some vector a bunch of times. That some vector could just be the first column of A, right? It can be arbitrary, so you might as well just take it to be one of the columns. So essentially what's going to go on in this algorithm is really just simulating that project algorithm that we already talked about, but doing it in kind of a clever factored fashion. That's basically it. Okay, it's just like one of these things that somehow ends up very, very elegant. So in order to prove that, so there's our algorithm. We're going to begin by proving a little lemma, and then we're going to use it in a way that like feels totally uncomfortable and weird. And I keep double checking to make sure my argument is right, because it's a little bit gross. So this is a fact that I think a lot of people might have like seen in a linear algebra class. That's just like a kind of a fun fact, but it's actually useful for our proof today, which is as follows. Let's say that I have 2 matrices A and B, and that they commute, namely that A times B is equal to B times A. We're going to, moreover, assume that they have distinct eigenvalues. So it turns out to be unnecessary here, but it just makes our proof easier. It's good enough. Then essentially, these matrices commute if and only if they have the same set of eigenvectors. They may have different eigenvalues, but they have the same set of eigenvectors. Okay? So let's prove this little claim really quick. So claim AB equals BA if and only if they have the same eigenvector. And subject to all the stuff on the screen there. I'm going to be lazy. Okay, so what direction do we want to go first? I don't know. How about right to left? So let's do the proof in this direction. So in other words, suppose we have 2 matrices of the same eigenvectors, and now we need to show that they commute, right? So in this particular case, take the eigenbasis. Well, in this case, it's the shared eigenbasis between A and B, so we're just going to we're not going to distinguish, right? We're going to call this x1 to xn, all of which are in Rn, right? So they have different eigenvalues, like maybe lambda 1 through n A and lambda 1 through n B. Cool? Now, 2 matrices are the same if when I multiply them against any vector, I get the same thing. That makes sense? This perspective, like if you take a differential geometry course, turns out to be sort of the way to think about matrices. Right, so in particular, let's say that I take just a generic y in Rn. Well, generically, I can take any vector in Rn and I can write it in my basis, right? So in particular, I know that like I can write y is equal to the sum ci xi, like that. Cool? All right, so notice what happens. Let's say that I have A times B times y. So this is A times B times the sum ci xi, like that. Cool? All right, I can take these two matrices and I can push them into the sum like that. So I'm going to have A times B times xi. Now what's B times xi? Well, xi is an eigenvector of B, right? That's right. So in particular, this is the sum ci lambda I B maybe times A xi. Yeah. What's A xi? Yeah, it's just another eigenvalue, right? Because it's the same eigenvectors for the two matrices. That was our conceit here. Yeah. So in particular, this is ci lambda I B lambda I A xi. And notice now I can just do the whole thing in reverse, but flip the which eigenvalue I do first, right? And what I'll get is that this is B A y. So what did we show? We showed for any vector y in Rn, multiplying AB by y gives me the same thing as multiplying BA by y. So in particular, they're the same matrix. Cool? Ta-da. Okay. The other direction is like mildly more annoying. So let's do that next. So in particular now, we have to show kind of the reverse, that like if my matrices commute, then they must have the same eigenvectors, right? So let's do that. This microphone noise is really irritating. Is there control for the volume? There's like this constant scrape in the back of my ear. There is not. Great. Okay. I don't even know what it's touching. All right. Right, so let's do the forward direction. So suppose AB equals BA, like that. Okay, and take AX equals lambda x. So take like an eigenvector of A. So we need to show what? That it's also an eigenvector of B. Yeah? Okay, so here's going to be our trick. Let's look at the product A times BX, like that, just for fun. Okay, so for one thing, obviously I can parenthesize this the other way around. This is AB times X. Well, our matrices commute, so we know that that's the same thing as B times AX, like that. Yeah? Okay, but we know that X is an eigenvector of A, so now we can do something with that, right? So in particular, this is B, AX equals lambda x. So this is times lambda x, like that. Cool? All right. So let's take a look. I took A and I multiplied it by bx, right? And what did I get? I got lambda times bx. Now remember our assumption. What did we assume? We assumed that our matrix has a full set of eigenvectors, and moreover, there is a unique set of eigenvalues. So there are no repeated eigenvalues. What can we conclude? This is a sneaky proof. Well, what did I just show? I showed A times bx, whatever that vector is equal to lambda times bx. I also know that ax equals lambda x, so necessarily, not quite, but that's pretty close, that essentially bx and x are parallel to one another, right? Because there's a one-dimensional space of eigenvectors. So basically we have two cases. The first one is bx is non-zero, right? So in that case, what we've basically shown is that bx and x are parallel to one another, right? So in that case, we have bx is, well, it's parallel to x, so there's some c where bx is equal to cx, but that's the definition of an eigenvector, yeah? So we can conclude that x is an eigenvector of B, which is what we wanted. Is that cool? Otherwise, what's the second case? Bx equals 0. But then we're actually done because x is an eigenvector with eigenvalue 0. You see that? So what have we shown? We've shown that we took an eigenvector of A, and then by kind of munging it around and using this like clever little commutativity relationship, we concluded that actually that eigenvector is also an eigenvector of B, possibly with a different eigenvalue, or it's just with eigenvalue 0. Sneaky, huh? This proof feels circuitous. It's one of those ones you have to stare at a few times, but it's not, I promise you. Any questions? Okay, so the high level, yes, on. Yes, yeah. But for this lecture, it turns out convergence of the QR iteration method needs them to be distinct anyway. So I might as well do the simplified version. Yeah. This is a well-known fact, and it also, like, it holds an extreme generality. If you look at like operators in physics, they also has a property like this. If they commute, they have the same eigen stuff. Yeah. Okay, so right, so that's going to be what allows us to begin to figure out why this QR iteration algorithm might have an interesting conversion point. So let's say that QR iteration did converge. Like, for whatever reason, I kept factoring QR and then RQ and then QR and then RQ and whatever, and that thing had a fixed point. We're not going to show yet that it actually does, but suppose that it did, right? Like, so in other words, I keep doing this procedure, and eventually Q converges to some matrix and R converges to some other matrix. I got lucky. By the way, you probably could argue that there's a convergent subsequence quite easily if you're an analysis student, but that's going to be irrelevant. Okay, so in particular, let's say that like these QIs eventually go to some matrix Q infinity, and the RIs eventually go to some matrix R infinity. This is just so that we can get some intuition for, like, if it were to converge, why would it reach the thing that we kind of wanted, right? So let's say that it converged. But what does it mean to converge in this case? Well, that means that basically the iterations don't do anything, right? So in other words, in that case, we have Q infinity R infinity equals R infinity Q infinity, right? Okay, so here's the kind of fun thing. So in this particular case, moreover, if we look at the product of Q and R, so let's call A infinity equals Q infinity R. If you're wondering, this is the part where I get uncomfortable because there's a lot of analytical arguments here that are like easy to get wrong, so we're gonna do it together, team, okay? So then, in particular, what do we learn? We learned that, right, so basically, if we go back to how we derived QR iteration, we see that conjugating by Q infinity doesn't do anything, right? Because remember, this is exactly RQ, right? So if it converged, then like essentially those two things are equal to one another. That make sense? Okay, so let's think about this for a second. Q is orthogonal. So this is not a thing we usually think about. Like, we don't usually think about the eigenvectors orthogonal matrices, like, because that's a weird object. But in this specific case, we can, because we have that funny theorem about commuting matrices. Well, notice R is going to have a full set of eigenvalues and eigenvectors, right? Because this is just coming from this QR iteration. And moreover, Q and R commute, so then kind of necessarily, Q actually has the same eigenvectors. Isn't this sneaky? Right, because that's sort of the byproduct of our proof. And so what is that going to allow us to conclude? So first of all, Q infinity is orthogonal. So we can say, well, any eigenvalue of Q infinity up to absolute value, and here this has to be complex absolute value for all we know, has size 1. Right? It's an orthogonal matrix. It doesn't affect the lengths of vectors. Okay? So we have the eigenvalues. Let's say that I have some eigenvector A infinity like that. Okay? So here's one thing that we can do, which is kind of sneaky. So A infinity is equal to Q infinity R infinity times X. Sorry, I'm going to kind of hopscotch our equal signs there. My apologies. Okay, but in this particular case, if it converged, then they commute, right? So I can flip the order of Q and R. Okay? Like that. Cool? Now here's kind of a weird thing. These guys have the same set of eigenvectors. Q has eigenvalues plus or minus 1. And moreover, just by definition of QR iteration, all these things are real objects, right? There's no imaginary part. So one thing that you can conclude is that well, remember that Okay, so if x is an eigenvector of A, it also has to be an eigenvector of these different pieces. In particular, R infinity, Q infinity, sorry, let me just abort that sentence and try again. Okay, if it converged, hopefully you guys believe me up to here, right? That like Q and R commute, I can take any eigenvector of A. Remember that A infinity has the same eigenvalues as what I started with. In particular, it's got a full set of eigenvectors. Okay, I get to this particular step here. Well, X is also an eigenvector of Q, right? This is what's going to happen. Basically, all of these objects are going to have the same eigenvectors, just different eigenvalues. And so when we put this all together, essentially what I'm going to conclude is that R infinity times X is equal to lambda X. Now, why is that going to be useful? Well, here's a really sneaky thing. R is upper triangular. So if QR iteration converges, I claim we can read off the eigenvectors of our matrix really easily, or eigenvalues really easily. Now, here's what I'm going to do. I'm going to do exactly what I told you guys not to do in the previous lecture, which is to do the sort of like college algebra way of computing eigenvalues. Let's say that I have an upper triangular matrix and I want to compute its eigenvalues. Well, what is the determinant of R minus lambda I for an upper triangular R? Well, if we think about it, let's just do this kind of pictorially. So I've got this diagonal set of values. I got a bunch of zeros. And now I'm subtracting off the lambda i's down there, right? Now, do you guys remember how the determinant formula kind of works here? Right? You take all these different products going all these different paths. Basically, there's only one path that's not going to involve some non-zero element here. That's the path right down the diagonal, right? So in particular, this is the product of RII minus lambda I. Oh, sorry, minus lambda. That makes sense? So this is the diagonal elements of R minus lambda. So what are the roots of this polynomial? Well, they're just staring you in the face. The eigenvalues of an upper triangular matrix are just its diagonal matrix, or its diagonal elements. So here's the kind of neat thing that happens in QR iteration is if it converges, then essentially Q doesn't do anything interesting. It's just flipping signs of stuff because of this commuting matrix property. And moreover, R contains all the eigenvalues down its diagonal. You can just ignore what's ever above the diagonal, and that's perfectly fine. So now what we need to argue is that that's like there's some world in which that conversion should actually happen. Yeah?
So if we're thinking about the complex numbers, it doesn't necessarily converge to diagonal.
Well, here's the thing. The actual QR factorization in every step of this thing can never give you anything that's complex, right? So like, it's this weird situation where you have two matrices that commute. They must have a full set of, basically, actually, if you look closely at our argument, if one of them has a full set of the eigenvectors, then the other one must also. So what do we show? We show that Q and R have the same eigenvectors. Moreover, those eigenvectors are real because they're also the same eigenvectors as A. That's what we started with, right? Right, so if you think about it, there's no kind of place in that calculation for an imaginary number to pop up. So you actually don't have to worry about the complex part. It's up to plus or minus. So it is true that one thing that can happen in QR iteration is that like the diagonal elements of R flip sign every step or something like that. But remember that we talked about householder factorization, which kind of doesn't mess with the determinant of a matrix. And that turns out to be enough to fix that particular issue. Yes?
I missed the justification of the step like equals plus minus R.
Yeah, let's see. That's because I fudged it a little. Let's see if I can manage to get it right here. So we take an eigenvector x of A, okay? So in particular, let's see. Give me a second here. I think I skipped a step and then I got myself confused. You guys are throwing me off, which is fine. Right, so clearly I can do up to here. These things are all fine, right? Because it commutes, all I did was substitute the fact that A is equal to QR, right? Now I commute those two, I get RQ. And now basically my point here, which I think I've managed to fudge.
We can argue Q transposes eigenvectors. So
Oh, yeah, yeah, okay, I'm sorry. Yeah, that's, thank you. So in particular, for this relationship here, notice that we have A and Q have the same eigenvectors, right? So we have like basically every possible object here has the same eigenvectors, right? So Q times X has to equal some multiple of X because X is also an eigenvector of Q. Moreover, Q is real, right? So that means it's basically plus or minus X, right? Yeah, and that completes it. Thank you, Nick. Yes. Ah, because they commute. Take this relationship here and pre-multiply by Q transpose. Yeah, sorry. I totally mangled that proof, and for that, I apologize. The good news is this is also written out carefully in the book. We're just following it step by step. Okay, so the good news is that up to your instructor getting confused because there's a lot of indices in today's lecture, essentially what we've justified so far is should this thing converge, the diagonal elements of R are going to converge to up to sign the eigenvalues of Q. Moreover, by choosing QR to preserve orientation in every step, you can kind of convince yourself that you don't need that minus there. So what's left is to show that there's any hope of this thing actually converging. and that's the part that I think is kind of interesting to think about. Now, essentially, there's a few calculations that we can do to kind of justify what's going on here. Now, here's kind of a fun thing. Let's say that I take a matrix A, and I multiply it by itself a bunch of times, like k times, okay? And I'm going to do kind of a funny thing, which is I'm going to just pick off one of these a's on the right-hand side. So in particular, this is going to be a to the k minus 1 times a bunch of vectors, which are the columns of a1, a2, an, like that. Okay? Now, generically, there are cases where this fails, but generically speaking, remember what happens. Well, okay, so if I take a matrix and I multiply it by another guy, this is the same as a to the k minus 1, a1, a to the k minus 1, a2, all the way a k minus 1, an, like that. Yeah? This is just a weird way to write a high power of a matrix. Now, let's think about what each of these matrices, what do each of these vectors start to look like? All of these begin to look very close to just the dominant eigenvector of A. Do you see that? Generically speaking, because, well, I took some vector, I multiplied by a high power A, and remember that's the whole point of eigenvector iteration, is that this thing just takes you closer and closer to an eigenvector, yeah? And so here's the kind of funny thing that happens. So like in particular, let's say that I took a to the k for a really, really large k, and then I took its QR factorization. Now, first of all, numerically, is this advisable? Absolutely not, right? Because like essentially everything is going to look parallel to everything else, and moreover, like this could be like a bunch of giant numbers for all we know, right? However, like if we forget about that for a minute, if I took QR of a to the k, what's going to happen? Well, let's think about the very first column. So generically, remember that I have Q and R. R has this triangular structure like that. So think about the very first column of Q. Well, remember the product of QR, let's do our matrix vector product, or our matrix product in this case, right? So I'm going to go down this way, across that way. What is the very first column of Q? Well, it's just the first column of a to the k divided by its norm. Do you see that? Why is that? Well, again, the triangular structure means that there's only one non-zero weight in the product Q times R when you multiply those two things out in the first column. Okay? So what can we conclude? If I take a giant power of A and I take its QR and I look at the first column of Q, what is that thing? It's just the first eigenvector. Sneaky, huh? Now let's think about the second column. Well, what is the second column? It is the, well, it's a giant power of A, but I projected out the first column. What's that object going to be? This is the second eigenvector. And so on and so forth. So essentially, here's a really terrible way to compute all the eigenvectors of your matrix, generically speaking, is to just keep multiplying the matrix by itself, take a giant power of that matrix, and then compute its QR, and the columns of Q will be roughly the eigenvectors of your matrix. Yeah, that's basically the fact that we're using today. And it comes from the fact that really this is just projected QR or projected eigenvector iteration in like a sneaky matrix form, right? Where like the first guy is just, I take a high power and then I divide it by its norm. The second one is exactly that, but I projected out the first and so on. And so what we're going to see is that QR iteration is basically just a numerically stable implementation of this algorithm. That's basically it. And that's what's going to justify that this thing actually really does converge to what we would hope. Okay? Yes?
Is the reason the previous eigenvectors are projected out because Q is orthogonal?
That's right. Q is orthogonal and R is upper triangular, meaning that like the second column of Q only involves the first two columns of A. Yeah. Or like if that's unfamiliar, remember our first derivation of QR factorization used this Graham-Schmidt algorithm. And what did I do in Graham-Schmidt? Like I first normalized the first column, and then I took the second guy and I projected out the first, and I took the third and projected out the first two. So if you think about it, like applied to this matrix, that's going to give you exactly the eigenvectors. Yeah.
Maybe a little outside scope.
Cool.
Is this going to be efficient at all? Because we have to like QR factorize with household.
Mm-hmm.
Maybe a lot of times.
Yeah. Well, so the question is, what's the alternative? And it's not actually that obvious, right? So yeah, it's efficient because we haven't really derived any other algorithm that's able to do this. But you're right, it's expensive. It takes cubic time per step of this method to run. Yeah, but eigenvectors are just expensive objects to compute. That's just generically true. Okay, so here's what we're going to do is we're going to take our algorithm and we're going to kind of expand it inductively. My apologies for mangling some of these explanations. As you can see, it's a little bit finicky and like I haven't had enough coffee this morning. So let's say that I took my original matrix and I factor it, and now I'm going to give indices. So I'm going to call this Q1 R1, right? So I'm going to use the subscript here to denote what iteration of my algorithm that I'm in. Okay? So let's say that I wanted, obviously I don't actually compute A squared, but suppose I had. I can substitute in Q1 R1 twice for fun. Yeah? So what is A squared equal to? Well, it's Q1 R1. Q1 R1, like that, right? I haven't done anything terribly prolific. Anybody have any idea for like a fun way to relate this to our algorithm? I'm going to interpret the gesture Hamid made as the right answer, which is if we look at the middle term here, what did our algorithm do? It took Q and R, and then it flipped them in reverse, replaced A by that, and computed the QR factorization of this object. So this is Q1, Q2, R2, R1. Everybody see that? Now you guys can probably see the pattern. Isn't this cool? This is so cool. This algorithm is just like hiding all kinds of different equivalent calculations in one. Okay, let's do one more example. What's A cubed? Well, obviously this is A squared times A. So I've got Q1, Q2, R2, R1, and now I got A, which the only thing we know about A is that it's Q1, R1. Like that. This feels kind of asymmetric, but it turns out we're going to be able to fix this. So notice R1, Q1 is the same as Q2, R2, like that, right? Now, notice I have R2, Q2 in the middle of my product here, right? So this is Q3, R3. So essentially, I showed that A cubed is equal to Q1, Q2, Q3, R3, R2, R1. What do we know about the product of orthogonal matrices? It's itself orthogonal. What do you know about the product of upper triangular matrices? It's itself upper triangular. So notice that secretly our QR iteration, it never actually computes A and A cubed and whatever. But it does compute each like Q1, Q2, Q3, Q4, Q5. So if I kept a running product of my Qs, I would have a matrix of eigenvectors. That's what we just showed, right? Because essentially, let me rephrase that. The running product of the Qs is basically the Q and the QR factorization of A to the K, right? And so like we argued on the board that I just erased, as I take QR factorization of A to the K for really large K, the Q begins to look like the eigenvectors of A. So implicitly, what that showed is that like this product here is really giving me the eigenvectors of my matrix as this algorithm runs on. Isn't that kind of cool? Okay, so by the way, I guess I didn't actually show you, but essentially what we've shown by induction-ish is that this is Q1, QK, and then we've got an RK to R1. So basically this is going to be our matrix of eigenvectors as k goes off to infinity. Cool. Okay, so we're almost done, I promise. You can put me out of my excruciating pain here. Okay, so our last little bit here is to show, so this actually already gives us one small edit to our QR iteration algorithm if we wanted the eigenvectors, right? Which is that we just look at this running product of Q's and that's good. But let's say that we only want the eigenvalues. I claim you can get that just from the diagonal of R, right? We mentioned that in convergence. Now let's show that like there's some hope of actually reaching that point. Now in particular, you're going to do a slightly different thing, which we're going to look at the iterates of the algorithm itself. Oh, God, put me out of my misery. I just want to do SVD. That's the easier one. Okay. And again, to reiterate, the book has this all very careful because I'm uncomfortable with this topic. So when I wrote it, I was super careful in the write-up to get all the indices correct, all that good stuff. Okay, so now let's do the opposite. So notice here we took high powers of A and we showed we can relate it to QR iteration. And that was enough to kind of justify that the running product of the Q's gives us the eigenvectors that we want. Now what I'm going to claim is that we don't even need to keep those around. We can get the eigenvalues directly from R. And let's do that as follows. So now, rather than looking at expressions for high powers of A, let's look for expressions of the iterates of the QR algorithm itself. So in particular, okay, we're going to say A, we're just going to call that A1 of our algorithm. Obviously, this is Q1, R1 by definition. Now, let's look at A2. Well, what is this thing? Well, it's R1, Q1, like that. Right? And if we kind of reverse engineer our proof from before, notice that that is the same as Q1 transpose A Q1, right? Remember, that was actually how we derived the QR iteration algorithm. We're going to do a couple more steps. You're going to see a cool pattern in RS. So what is A3? Well, it's R2 Q2, like that, again by definition. Okay. Well, what can we do here? Well, this is the same as Q2 transpose A2 Q2, right? Because that's how we got QR iteration, again, just like the previous line. But now we have this expression. So this is Q2 transpose Q1 transpose A Q1 Q2. Does everybody see how I did that? Okay, so generically speaking, what is AK? Well, it's going to be Q1 to QK transpose A Q1 to QK. Right? That's essentially inductively, if we follow this argument, this is what we've shown. Now, my argument about Q infinity and R infinity was clearly a little bit fudged, and for that I apologize. But the good news is we can recoup it now. Why is that? Well, essentially, what did we argue so far? Well, up here, essentially we showed 3 steps in a row. The first was that if we take a big power of A and we compute its QR factorization, that the Q is going to give us the eigenvectors of A, right? That was thing 1. Thing 2 is that we actually have the QR factorization of that big power of A kind of hiding in our QR iteration algorithm if we kept like a running product of our Q's, right? That's what I proved previously. Now there's one third thing, which is that secretly, if I look at A sub k, right, that's like the current version of A that I have in my algorithm. Now, I haven't actually written, like, this isn't how we compute it, but behind the scenes, we just showed that it is equal to taking the original A and conjugating it by the product of all the Q's we've seen so far. Again, this isn't how we actually compute it. This is like a fact about the A sub k. Does that make sense? Well, what did we show on this previous board? We showed that this thing, well, this thing goes off to the matrix of eigenvectors, right? So this goes off to eigenvectors, like that. Now, if I take symmetric matrix and I conjugate it by its eigenvectors, what do I get? We showed this in the last lecture. I get a diagonal matrix of eigenvalues. All right, so now we're done. Do you see that? Because essentially, what did I just show? Well, I showed that in QR iteration, secretly, the sequence of A's that I compute has this alternative form. I didn't actually compute it this way, but like I could have, right? Which is that they're essentially the A conjugated by the running product of the Q's, right? We showed that these things approach the eigenvectors, which means that this product approaches a diagonal matrix of eigenvalues. Isn't that cool? I think this is the coolest thing ever. So essentially, what does this show? This shows this QR iteration algorithm. What is it doing? To kind of summarize our story. Well, really, we're just conjugating by Q a bunch of times, where the Q is changing because our matrix is changing. And moreover, the matrix that we have is really just the original guy conjugated by the whole sequence. That's what we've shown here. Moreover, we argue that the whole sequence of Q's, if you multiply them all together, converges to a matrix of eigenvectors. So when we glue all those facts together, what we've shown is that A is just going to converge to a diagonal thing of eigenvalues. All right, I'm going to move on quickly before you guys find a hole in my proof. But essentially, that's our argument here. At least for symmetric A with non-repeated eigenvectors, what we've shown is that, or eigenvalues rather, essentially up to sign, this algorithm is going to converge to a diagonal matrix of eigenvalues, and that's super cool. And that's essentially what we use to compute eigenvectors. In practice, when you look at like code in a lot of linear algebra software, it's basically just this algorithm. Now, we asked about efficiency. You're absolutely right. So this algorithm is extremely inefficient in the sense that like computing QR of a generic matrix takes cubic time. It takes a lot of space. Then we have to do the product that also takes cubic time, usually. And so because of this thing, the way that we've written it is quite slow on your computer. So for matrices of size up to like 500, this is probably okay. After that, it starts to become like a problem. You look at me like this for 500, but we're like not in Pentium times anymore. Like processors are pretty good. Okay. However, it turns out you can do better. So if you want to read about advanced versions of this algorithm, like I mentioned, essentially what usually happens is before you do QR iteration, you reduce your matrix to tridiagonal form. And then what you can show, kind of similarly, like in the homework we did LU factorization specifically for tridiagonal matrices. Essentially, like there's very nice versions of QR and everything else for that specific kind of matrix that allows you to avoid some of the computation we've done here. But the basic proof and idea behind these is exactly the same. It's basically just a change of variables like Alice suggested. If you want to dig into eigenvalue problems, you could easily teach an entire course on just those. These turn out to be like really, really hard. As you can see, it's like one of these algorithms where every single one of the eigenvalue algorithms I know of out there is basically some variation of the very first thing we covered, which is if I take a vector and multiply it a bunch of times by a matrix, I get the principal eigenvector. All of them are just variations of that story. But that story gets really complicated. In general, if you kind of dig any deeper than what we've covered in class today, what you're going to come across soon are methods called Krylov subspace methods. And I encourage you to take a read on those. They're really cool. For example, there's some Krylov subspace methods that do something that I consider really wild, which is they work from the outside of the spectrum in. So you get like the biggest and the smallest eigenvalue, and then like it kind of progresses inward. If you're curious, the Krylov subspace is defined to be sort of the span of like some vector x, a squared x, so on up to a to the k x. Right? And it turns out that like this set of vectors obviously has a lot of nice properties. Like if I orthonormalize them, then like that guy is going to look awfully close to an eigenvector. A question you might ask is if I stop at a particular k and I orthonormalize just the last n of these things, right? Then like what we kind of argued in this class is that in the limit that looks like the set of eigenvectors, you might ask like what is the relative error of each of those? Because obviously as I go farther back in the sequence, it gets worse. But anyway, those are the kinds of fun questions you can think about. Yes?
Does it converge? And then how do you measure convergence in practice? Like, do you take like off-diagonal part of R and just check how close it is to 0?
That's a great question. So the question is how fast does this thing converge? And when are you done? Yeah, so I think in terms of, let's answer the second one first, which is that we know basically that what should happen eventually is like I do QR, I replace it with RQ, and when I look at that product, it'll become diagonal, right? So a very reasonable heuristic would be to look at the off-diagonal elements and stop when they're close to 0. That's, I think, roughly what people do. There's a different question you could ask, which is like, how quickly should this thing converge in theory, right? And remember, eigenvalue iteration is a little bit tricky. So essentially, the convergence has to do with how similar the eigenvectors are to one another and how close together the eigenvalues are. So when the eigenvalues are very well separated, this algorithm tends to converge very quickly. When they're not well separated, it tends to converge kind of slowly. If you want to know about the specific convergence rate, I think what you'd have to, I think it has to do with this, it's like has to do with the range of eigenvalues, and I always forget if it's the gap between the first two or the last two when you talk about QR. But it has, but if you essentially if you look at the gap between any pair of eigenvalues, if you think about it like the argument that we made in our last lecture about convergence for the algorithm where you just look at the first eigenvector still kind of applies, right? Because essentially this orthogonal step is just taking one eigenvector and projecting out the next one. So I believe if you look at all of the successive pairs and you look at the ratios and you like compute the biggest one or the smallest, that tells you something about convergence, but I'd have to think about it a bit. It's a good question. Okay, so one thing that the book covers that we're not going to have time to cover today, because I would like to be done with eigenvalues, please, is conditioning of this problem. So essentially, there's a calculation in there that you guys should give a read to, which looks very similar to the calculation we did for conditioning of linear cells in class, which is to try to ask, like, well, as I perturb my matrix, what happens to the eigenvalue and eigenvector? These calculations are a little bit hairy because specifically in the case where eigenvector or eigenvalues are repeated, the differentiability of this is like a little bit suspect, right? Because you can choose any set of vectors in that subspace that is equally good from perspective of eigenvalue problem. And so it's not clear that it is differentiable in that case. And so doing that calculation carefully requires a little bit of careful logic. But the basic reasoning is the same. We start out with like our ax equals lambda x. We kind of do this Taylor series relationship and expand back out. So I'll let you guys take a look at the book for some reasoning there. Essentially, I think what you're going to find is that you can look at the eigenvalues of A and the eigenvalues of A transpose, and what you'll find is that the problem is best conditioned when those two things are close to one another, or eigenvectors rather. Right? So for asymmetric matrices, they do not have to be the same. Right? There's something called a left and a right eigenvector. And so to first order, it turns out the conditioning of the problem has to do with how far apart those two sets of eigenvectors are. There's a different question which says for a symmetric matrix, how does conditioning work? So there I'm not concerned about left versus right. And that's a trickier calculation. So we'll save that for later. Incidentally, this calculation feels like fun trivia that like some annoying numerical analysis professor wants to do. And I think that was true until about 5 years ago. So these days, there's a very common computational pattern in machine learning where you're like building up a graph and like a matrix of some sort. And at some point in your computational chain, you compute its eigenvectors. This turns out to be like a pretty common thing in graph theory. And so for like certain neural network architectures that involve graphs, there actually is some link in the chain that involves an eigenvector problem, which means you have to be able to differentiate through it in your backprop algorithm. And essentially, if you look at the ways that we derive condition number, like what is it? It's how do eigenvalues and eigenvectors change as a function of perturbations of your matrix? It's exactly that calculation you do when you backprop through eigenvector problem. So if we read these calculations from another lens, it's also the way that you would derive backpropagation rules for exactly the calculations we've done here. So maybe I'll have you do it on the exam. That would be fun. Okay. Just to convince you guys that it's useful for machine learning. Okay. So in any event, with that, let's please put your instructor out of his misery and go back to more comfortable ground. And in particular, we will talk about one more matrix factorization that I really wanted to get to today because it is in your homework in a little tiny bit. And that's something called the singular value decomposition, or SVD. SVD, unlike eigenvector decomposition, is a decomposition that exists for any matrix, right? So far, like we have this kind of weird story for eigenvectors, which is that they often exist, like for symmetric matrices they do. But for asymmetric ones, we don't really know when they do or don't exist. And for matrices whose rows and columns aren't the same, then like it's all kind of irrelevant, right? And so SVD is kind of like the closest projection of an eigenvector problem onto like, if you want something to work for every possible matrix. And it's also the sledgehammer of numerical linear algebra. In general, on exams, on homework, and in life, when encountered with a linear algebra problem that is unfamiliar, the very first thing that you should do is drop in the SVD and see what happens. Just like as a life philosophy, that should be the first thing you should do. Okay? And so like anytime you are stuck on a homework problem, including on this homework, or in many other contexts, the SVD probably solves your problem, especially if there's an L2 norm hiding in there somewhere. Now, it might not be the most efficient way to solve your problem, but it'll probably solve it. Incidentally, in life, if you're encountered with a convex optimization problem, you should compute its dual, but we'll save that for another class. Okay, so we're going to talk about the SVD, and there are so many ways to motivate the singular value decomposition. Now, I was flipping through the linear algebra class textbook that some of the classes here use, and it does a really sad thing, which is the usual, like, one interesting fact about matrices is they admit a factorization of the form U sigma V transpose, which I think is like the worst possible way to motivate this. So we're going to try a bit of a geometric approach and kind of see that the SVD arises very naturally. And that's to look at a particular object that we've kind of alluded to called the Rayleigh quotient. So there's like a particular picture that we all draw in linear algebra class, but I don't think we think about it too hard. It just follows. So now, finally, we are out of the universe where we need all our matrices to be symmetric and positive definite, whatever. So now we just have a generic matrix A in Rm by F. Okay? And let's think about a matrix as a thing that acts on vectors, right? So if I have a matrix A in Rm by N, then what is the input to A? Just to sanity check our indices really quick. What space will that be in? Rn, that's right, because remember, it goes this way in products. So I have whatever, Rn. And in fact, I'm going to draw everything two-dimensional today because boards are flat. But you can tell it's n-dimensional because I wrote it there, okay? And then what does A do? Well, it maps it to some other space, Rm, like that, right? So I take a vector V, I multiply it by A, and I get something in another space. And a very typical thing you might do is ask about, like, well, what is the geometry of a linear map? Like, in particular, I think there's this picture that we all draw kind of reflexively. It looks something like this. I draw a circle here, I map it through, and I get some like kind of sheared ellipse. And I think a reasonable question that we often don't think about very critically is like, why? Yeah, I mean, for all we know, if all I give you is this linearity property, like it all feels very natural that this should be the picture, but for all we know, we get like a star or like something like that. Like there's no reason why I should take a circle and map it to an ellipse a priori. You have to prove that kind of thing, right? And in particular, one way that you might do it is we look at these pictures and oftentimes we kind of say, okay, well, we might like draw these things like the major and minor axes of the ellipse and kind of ask what happens there, right? And what are these things? Well, if I kind of think of this as like a function on the unit sphere, then these are like the points that are like the farthest away or the closest to the origin. Does that make sense? So that motivates us to study optimization problems of the form. And maybe I want to look at kind of this ratio, which is the norm of A times V divided by the norm of V. Right? And like the critical points of this functional is sometimes called the Rayleigh quotient, like somehow tell us something about the geometry of A. Notice that I am no longer requiring these two things to be in the same space. One could be in Rm and the other in Rn. You know? Okay, so let's say that I want to like look at critical points of R. Well, conveniently for us, that is going to lead us to exactly the same optimization problem we've written like a billion times. Right? Notice in this problem, if I scale V up or down, nothing changes. Right? So in particular, for example, I could look at maximizing over all of V, the norm of A times V, subject to the constraint that the norm of V is equal to 1. And hopefully you guys see that this and the Rayleigh quotient have the same maximum, right? Okay. So I think we have now proven in this class about 78 different ways that this optimization problem leads to an eigenvalue problem. Does anybody remember what it is? Oh, you're killing me. Literally anybody, please raise your hand. Put me out of my misery. Yes? Almost, but remember A is non-square. Like what happens when I differentiate this guy? Maybe I square it like that. That's exactly right. So what I'm going to get is A transpose A, V equals lambda V. Okay? Notice that this is a square matrix, even though I started with something non-square. Right? This was from a few lectures ago. Okay, so here's what we're going to do. We're going to show that this, notice that somehow, what is it suggesting? So let's think about what is V. V is like here, right? And then like AV is going to be like there. Notice that these are in different spaces. So like the A transpose A is kind of like mapping me here and then mapping back. right? But let's say that we didn't do that. Let's say that we computed one of these critical points v, and then we look at just a pair of v and av, and we kind of ask about the relationship. Does that make sense? By the way, notice that lambda here is very clearly greater than or equal to 0. Okay. So that's what's going to lead us to the SVD, is the idea that like we look at critical points of this functional, like length, and then what we're going to ask is basically like, what are the relationships between those critical points and their images in the other space, where now those things are in two different spaces, right? One is in Rn and one is in Rm. Yeah? And we do kind of a sneaky thing, which is to actually solve the critical point problem. Notice that we get an eigenvector, but it's not of A, it's of A transpose A. Okay? So let's say that we take a basis. In particular, A transpose A, this guy is a symmetric matrix, so it admits a full orthogonal eigenbasis. This is the spectral theorem. So we have A transpose A times Vi is equal to lambda I times Vi, like that. Okay? Here's what we're going to do. I'm going to define a particular object. I'm going to call it UI star. I'm putting this star there because I'm going to normalize U in a minute. I'm going to make it unit length, but originally we're not going to do that. And I'm just going to call it A times Vi. That make sense? Now, why would I do that? If you think about like what are the V U pairs here, it's kind of like the point that maximizes distance from the origin and its image in the other space. That's kind of the objects that we're looking at here. Okay. So now I'm going to do something really cool. This is such a clever little observation, whoever thought of this. So let's say that I look at the following thing. So we have A transpose A times Vi is equal to lambda I Vi, just like before. Well, now we've given this thing a name. So we have A transpose times Ui star is lambda I Vi, like that. Yeah. I'm going to take this relationship, I'm going to pre-multiply it by A. So we started by A transpose A. Now I'm going to have AA transpose. We have AA transpose times UI star. Well, that's equal to lambda I times A transpose Vi, like that. Oh, sorry, AVI, that's right. Thank you, because I was about to panic. And what is AVI? Well, it's UI star. Thank you. I'm like really struggling today. I'm sorry, I should have had more coffee. What did I just show? Do you see this like kind of cool relationship now? I'm like starting to glue these spaces together. So on the one hand, I started with an eigenvector of A transpose A. And now I showed that that translates almost. I'd be a little bit careful about like if I got a 0 here. We'll come back to that in a second. But assuming that UI star is not equal to 0, what did I show? I showed that UI star is actually an eigenvector of AA transpose. So there's like this two pairs of matrices. Notice that their dimensionalities are not even the same necessarily. A transpose A and AA transpose. And behind the scenes, their eigenvalue problems are very cleanly linked together. This is so beautiful. Moreover, notice that they both have full sets of eigenvectors because these two matrices are square and symmetric. Cool? Okay. So what are we going to do? Well, we're going to keep deriving some more fun relationships here. So in particular, we showed that UI star is either an eigenvector of AA transpose or UI star equals 0. Yeah, those are basically our two cases. Okay. By the way, what is the norm of UI star? Well, it's UI star transpose UI star, like that. But remember, by definition, that's Vi transpose A Vi, like that. Cool? What's A transpose A Vi? Well, we've got a lambda there. So this is just lambda I. Okay? So notice, like slowly we're starting to glue these problems together, right? So now what do we know? We know that UI either corresponds to a 0 eigenvalue of our original problem, or it's also an eigenvector of this other matrix. Cool? So basically, if you like step back, by the way, notice that this means the norm of ui star is the square root of lambda I, right? Because there's a square on the left-hand side. So basically, like the little proposal, the idea that I'm trying to share here is that essentially there are these two eigenvalue problems, one for A transpose A and one for A transpose, that are looking at critical points of the length of a vector as it gets mapped forward and backward through my map. These things are linked together, and moreover, they have this more or less the same eigenvalues up to the kind of fact that m and n don't match, so there's some zeros that we need to fill in. I know the class is over. I'm going to spend one additional minute. If you guys want to leave, that's fine. Okay, so essentially, what have we shown? Well, okay, we have a bunch of different relationships here. We have A transpose A times VI is equal to lambda I VI. I'm rushing through this because I don't want to have to reconstruct it for like the first half of the next class. We have A transpose times UI is equal to lambda I. Now I'm going to normalize the UI stars. I'm going to divide them by their norms. We have A VI is equal to the square root of lambda I times UI. That comes from the norm calculation we just did. We have A transpose UI is equal to the square root of lambda I VI. And finally, UI transpose A times Vj. This is the one thing that we haven't done yet. Right, this is just a summary of our calculations so far. Well, what is this thing? Well, this is A transpose UI transpose Vj, like that. Well, from this earlier relationship, this is the square root of lambda I Vi transpose Vj. Well, now we're back in one of these eigenspaces, right? So this is either 1 when Vi is equal to Vj or 0 otherwise, right? So this is square root lambda I times delta I equals j. Okay. So we have two different orthogonal bases, one for A transpose A and one for A transpose, and they're linked together with a bunch of different relationships we've just derived here, right? And this just has to do with essentially the amount that each of these things gets scaled when they map to this other space. Does that make sense? So, almost done, I promise. Oh no, I know I'm over time. Let's define a matrix U bar, which is like U1, U2, and so on, and same thing for V bar. Then essentially, what have we shown? Well, if we take these relationships here and we just codify them in matrix form, what we're going to get is U bar transpose A, V bar is equal to a diagonal matrix. Do you see that? Because essentially, that's what this final relationship is showing. So what did I do? I took all my U's and I put them into a matrix, and I take their dot product against each of the AVs, and I got either 1 or 0, which gives me this sigma. So with this, we're going to basically end our lecture, but my point here, now I have to be a little bit careful. The columns U and V are orthonormal to one another, but I have not shown they make a full basis. Right? In particular, I had to discard 0 eigenvalues to get this little argument to work. But one thing that I can do is I can just take U and add additional columns to span the remainder of the space, and similarly for V. And when I do that, we're going to finish, we'll do this argument next time. In that case, I can take U and kind of expand it to be a big square matrix that's orthogonal, and the same thing for V, by just adding columns to span the rest of the space. If I do that, then I'm going to get a different factorization, which is what we'll start with next time, which is that A is equal to U sigma V transpose. Now, I rushed through this, and I promise next time we'll do it a little more slowly. But essentially, my point here, to give you a little bit of intuition and some help for your homework, is that I can take any matrix, and I can look at the eigenvalues of like A transpose A, the eigenvalues of A transpose, eigenvectors rather, and stick them in two matrices. And if I conjugate by that, I'm going to get something diagonal. So this is very close to the eigenvector problem. It's just that the thing I conjugated on the left and the right no longer agree. And moreover, the columns of these things are just critical points of length as I look in different directions. Cool? That'll be enough to do your homework. I see you. We can talk after class. Sorry to rush a little bit, but I did want to get to this expression so that you have everything you need. So with that, I will see you on Monday.
Is this?
Oh, that just says it's 1 when those numbers are equal and